Excellent, thank you. We have Professor Inal from KAUST, who is going to talk about a rather different approach, much more into the into more of the bioanalytical area, and talking about organic electronics, where she's a super expert in. So, Sahika, I look forward to learning more about your most recent research.
Thanks a lot. Thank you, Antje, for this kind introduction, also the kind invitation. I'm very happy to be talking to a different community. That's always a challenge, but hopefully today I will try to give you some introduction to the field of electronic devices that are made of organic electronic materials, and how we are using these devices for as biosensors. And for today's talk, I selected one particular application, and that application is for protein detection. Okay, so here we go. So for those of you who don't know, organic semiconductors are these type of organic molecules that contain typically an aromatic structure that allows for electron hopping. So you either have electron or hole hopping. You either have these small molecules or they are in the form of polymers with long chains. But what we have is an extended delocalized pi electron system. And these materials all have a band gap so that they have a semiconducting property. You can dope these materials with certain chemical dopants, or you can do electrochemical doping, as I'm going to show you in a bit, that allows them to go into a conducting state. But besides this conductivity property, they have a unique set of properties to build electrochemical devices, which operate in aqueous environments, as well as at the interface of really living systems like living cells or lipid bilayers and such. And I'm summarizing here a few of the properties. I don't have much time today. I know to go into the details, but for today's talk, I will highlight one of the properties that these materials have. It is their mixed charge transport property, meaning that in addition to conducting electronic charges, like other metals or metal oxides can do, these materials also transport ionic charges, which give them a very interesting channel for communication with biological systems. Because remember, in biology, most of the events, most of the signals are of ionic origin. So cells, for instance, use ionic charges to communicate with one another, or we have always ionic fluxes that is a result of certain biological events. And now if you have an electronic material that can understand these ionic fluxes, that can get affected by these ionic fluxes and convert these into an electrical signal, you can make really good sensors based on these devices. Now, let me tell you a little bit more about this mixed conductivity in conjugate polymer films, which will be important when I tell you the operation principles of the biosensors that we use. Now, this is how a metal would charge if you would put it in an electrolyte that contains ionic charges. In this case, this is a metal that conducts electrons. So if you put this in an electrolyte and apply an electrical field, you will see that there's a two-dimensional coupling between electrons of the metal and the cations of the electrolyte taking place. So there's an interfacial charging taking place in a regular metal. When you do the same thing in a conjugate polymer film, the situation changes because these polymers, some of them can uptake these ions into their volume and couple with electrons throughout the bulk of the film. So instead of limiting the charging, the electron or hole generation at this interface, because the material has a certain porosity and affinity to these ionic charges, you can have electronic charge generation throughout the whole bulk of the film. So they do support electronic charge transport along the conjugated backbone, as well as allowing for ionic charge transport through their bulk. So this means as we increase, for instance, the size of this polymer film that we make in the electronic device, you do get a higher capacitance, and this capacitance scales linearly with the volume of the film. So conjugated polymers are volumetric capacitors. And this is quite an important property because this means when there's a biological event takes place, which causes a flux of ions in the electrolyte, now your material will be very sensitive to these changes because its conductivity, its impedance, its capacitance will change dramatically as the ion and electron interactions take place in the bulk of the film. So we design biosensors such that the biorecognition event changes the ionic flux, and we can see this via an impedance change in our conjugate polymer film. And there's one electronic device type that uses this large change in the volumetric capacitance of the film, and it's called the organic electrochemical transistor. Now, the organic electrochemical transistor is a 3-terminal device that uses the conjugated polymer, this organic semiconductor film, in the channel. And this channel is covered with an electrolyte, an aqueous electrolyte. This can be the blood, the saliva, or any relevant biological medium that you are interested in analyzing. And here we have a third electrode, that's the gate electrode to finish the transistor circuitry that's connected to the source contact. Now, when there's a small ionic flux taking place in this solution, these ions will be penetrating, the ions of opposite polarity will be penetrating to the conjugate polymer film and causing a large change in the current that is flowing in the channel because of this volumetric capacitance of the conjugate polymer films that I mentioned. So we are using OECTs most of the time as the building block of our sensors because these devices are converting directly an ionic signal into an electronic output. And because they are transistors, inherently, they are acting as amplifiers. So they do amplify these local signals arising from ionic fluxes. And we do define the performance of OECTs because you can make various OECTs containing different types of conjugate polymer films by looking at their transconductance. This is the change, this is the magnitude of how much of a drain current change you will see as you have a small modulation at the gate electrode. So you can think that this gate electrode modulation as a biological event, the transconductance, if the transconductance of your device is high, that means you will see a high change in the drain current. And again, we are able to modulate the transconductance of these OECTs by changing their geometries. If you make, for instance, thick films, because of this volumetric capacitance, you will see that the transconductance will increase as the film thickness in the channel increases. Now, during the past decade, the potential of OECTs have been demonstrated in a variety of biosensor applications. For example, in one application, they have been used to detect neural signals, because when a neuron fires, this causes a change in the ionic flux. In an electrochemical transistor fabricated, a micron scale one, fabricated on a flexible, a conformable paralleling substrate, placed in the cortex of a rat, can record, for instance, epileptic seizures with very high signal-to-noise ratios. In another application, they're used in an impedance sensing mode. For instance, you can grow cells on top of these transistor channels, or you can put lipid bilayers that will initially block the ion flow in this electrolyte through the semiconductor channel. And by looking at the changes in the drain current, you can understand, for instance, ion channel activity that is integrated into these lipid bilayers, or the barrier tissue properties, the health of the cells that are integrated, that are placed on top of the transistor channels. Another popular application that we also like using transistors a lot is for detection of analytes. If you functionalize the gate electrode component or the channel as well with a biorecognition unit that is specific to a certain analyte, as this analyte binds to either of the transistor surfaces with the electrolyte, it will cause a change in the transistor operation. Therefore, the current that, for instance, you will detect from your device. And it's actually for this application, I will show you a few recent works that we have accomplished using OECTs. So my group at KAUST is called the Organic Bioelectronics Lab. As hopefully I managed to give you an introduction, a very brief one, to this field. We do look a lot at a lot of work on understanding the fundamentals of mixed ionic and electronic charge transport in conjugate polymer films. Within the context of mostly organic electrochemical transistors, we make micro-scale devices and collaborate with polymer chemists and look into how we can improve the transconductance as well as the transient response of these devices using polymer chemistry, doing some changes in the conjugate polymer backbone or the side chains and how these affect the mixed transport. And this becomes quite interesting because we do find very peculiar polymers, which are then using these peculiarities for biosensor designs. Which I showed you some examples, so I'm not going to get into detail and jump right into the application that I want to talk about in the next 15 minutes. Now, this application is something that obviously has affected everybody's life in the past 2 years. COVID-19, I think, has really revealed a gap in our diagnostic toolbox, and especially in the beginning of 2020, we see that we are really limited in the way how we detect pathogens as well as proteins. And I'm saying the protein as the target because the protein is something that you can find in the outer shell of this virus. So the standard method that we use is RT-PCR, and we do use RT-PCR because it is quite sensitive. You can go down to concentrations of attomolar ranges, which is why with RT-PCR one can detect the virus at its onset. RT-PCR is good, it's very sensitive, but at the same time it relies on enzymatic amplification effect. That's why it's sensitive, but this process is quite slow. And it will require a specialized lab because you would need to extract the RNA, for the virus from the interior of the pathogen. And that requires several chemicals and then processing techniques, and it takes quite some time to get to these results. Therefore, now we do have these lateral flow assays that are similar to the pregnancy tests that are used. These lateral flow assays looks at antigens, typically either the spike protein that is covering at the outer shell of the virus, or the N protein that is a bit inside the virus. So you still need to lyse the virus to reach those proteins. But these are quite fast tests, so it takes about 15 to 30 minutes to get a result. However, their sensitivity is not very good. So although, again, they're fast, the sensitivity is not good. You can detect only around 10 to the power of 7 copies per milliliter of sample. That means they can only detect the patients at the moderate or high infection levels. And that's not something that we want if we want to diagnose as early enough and start doing contact tracing. Therefore, I think what we are really missing is a method that can go maybe even single molecule levels, that can do detection in unprocessed samples, ideally maybe raw saliva, maybe not even nasal swabs that are typically used, or the throat swabs. It would not need an infrastructure, so you should be able to detect with even at home on experienced users. And obviously, it has to be fast so that it's useful. So in this speed and comfort again should not come at the expense of sensitivity, and of course, all of this should not cost a lot. And we thought the OECTs, due to this high amplification properties that I mentioned to you in the beginning, this volumetric conduction and high transconductance, they're very good high gain transducers to be used for protein or antigen detection. And they can do this detection in very short times if you can optimize the device operation properly. And that's something where we spend a lot of effort in building. But OECTs on its own, even though you can make them highly sensitive, to make them selective, you need a component, obviously, to functionalize with the biorecognition unit. And most of the times, people do prefer functionalizing the channel of electrolyte-gated transistors as the OCT. But in this work, we wanted to choose another approach. We wanted to use an external gate electrode for functionalization with the biorecognition unit, so that you can use the expensive part of the device, that's the transistor channel, and I'm showing you here like 6 identical channels, as the stationary component, so that you can do multiple measurements using the OST channel, but all you need to change is the gate electrode that's actually doing the sensing event. Now, our gate electrode is basically a gold electrode, that's a gold that is sputtered on top of a flexible substrate in millimeter scale that I'm going to show you a few pictures in a bit. And one trick that we do, instead of using typically an antibody for spike protein detection, we are using a very small version of these antibodies that is called a nanobody. And the reason for that is if you use a nanobody, which is quite small, you can populate a lot of nanobodies on a small surface of your sensor. And the more nanobodies recognition units you will have on the surface, obviously you have higher chance to pick up more target proteins. And the second trick that we do, instead of anchoring this nanobody directly on the surface, which would be affecting its performance because you would need some chemical modification done on the nanobody, we instead use a bio self-assembly module where the nanobody is synthesized with a module that we call spike catcher. And this extra protein is then linked to a peptide, and this peptide is covalently binding to a chemical layer that we assemble on top of our gold gate electrode. And the result is, as I'm going to show you, is quite a fast, sensitive, and selective, and mostly reusable because we separate this gate electrode component from the transistor in a very modular device because we could use different nanobodies that are synthesized against different targets. Now, let me show you a bit and give credit also to my colleagues who are the biochemists biochemistry group here at KAUST that are making this chemically unmodified nanobody, which we anchor on top of our gold electrodes at a very high density at the order of 700 micromolars. And we do get to these numbers and characterize the field characterization techniques to understand how much of these nanobodies we have on the gold electrode surface and whether these multi-level functionalization is working properly by using typical techniques such as cyclic voltammetry, impedance spectroscopy. Both of them are showing us that as we anchor the nanobody, the final layer is always giving us higher impedance and lower current from the gold because the nanobody is covering the surface properly. And we also do some physical chemical analysis like XPS to look at the surface groups that are in our final assembly. And another technique that's called quartz crystal microbalance with dissipation monitoring that allows us to calculate the number of nanobodies and their density on the gold electrode surface. Now, through these techniques, once we verify that we can build this multi-chemical and bio assembly layer on top of our gold electrode surfaces in the density and the orientation that we want, we go ahead and start assembling the sensors. Now, this is how the sensors that we build operate. So this is the gate electrode of the OST, again, an external gate electrode, which we expose to the patient sample. And this is about, this can be patient saliva that is unprocessed. It's just mixed with a buffer that we produce in the lab, about 5 microliters of it. We just put it on the gate electrode surface. Next thing we do, after 10 minutes of incubation, we rinse off anything that is unbound by using PBS. And afterwards, we just take the gate electrode and flip it and put it on top of the transistor base. And the two now, the only contact between the two is the electrolyte that we use. And this could be simply a salt solution like sodium chloride of even 0.1 molar concentrations, then we go ahead and start measuring the transistor characteristics. Now, how do these devices work and what do we rely on? We rely on the fact that once the binding of the protein takes place, there's a change in the impedance characteristics of the gold electrode. The capacitance of our gate electrode decreases continuously as more of the protein binds to the surface. And initially we are using a GFP nanobody, green fluorescent protein nanobody, as a model system, and GFP as the target to characterize the performance of these devices. And as the gate electrode capacitance decreases, this modulates how much the current we are modulating in the channel. So it affects the ionic flux and how much ionic flux the channel feels. And because the devices are very sensitive due to their high transconductance, we do see very few binding effects that causes normally very small changes in the gate capacitance as they cause a large change in the drain current that is flowing. And to be able to do that, again, we need to go to polymer chemistry and build devices that have very high transconductances. And we get these materials from Ian McCullough's group at Oxford. And these materials, these organic semiconductors, give us devices that have very high transconductances and very steep, what we call sub-threshold slope, meaning that very small voltage changes at the gate electrode will cause a very huge change in the drain current. So we specifically engineer these polymers and use them in devices. Now I'm showing you what is happening to the device that we functionalize with a nanobody that is expressed for SARS-CoV-2 spike protein, that's the coronavirus, and the spike protein of the coronavirus. So this is the device characteristics, drain current that we are measuring as a function of gate voltage that we apply. As you see, as the gate electrode is exposed to solutions that contain more and more of the spike protein, you see a drastic change in the transfer characteristics of the device, the current that you measure from the device. If you expose the same gate electrode to green fluorescent protein of equivalent concentrations as the spike protein, the changes that you see are very nominal, minimum. This shows the selectivity of the sensor, and it's very high sensitivity. Now, the sensitivity is arising, we think, not only because our transistors have very high transconductance and they have an optimized geometry for maximum amplification, but it's also because of the gate electrodes that we use, which have very dense immobilization methods where we don't really do anything again to the nanobody, and you have lots of nanobodies that is covering the gate electrode surface as an exceptionally high density. And these are the results of the sensor for protein that we spike in patient saliva samples. So obviously these are artificial samples that we generate, but the saliva is not artificial, so that we get from volunteers. And this is the sensor response. So this sensor is a SARS-CoV-2 sensor that we first exposed to non-target proteins such as GFP, as well as MERS-CoV S1, another coronavirus type. As you see, the sensor is not showing in response to these non-specific targets, whereas as soon as we use spike protein or the binding domain of the spike protein, there's a huge change in the sensor response that scales with the concentration of protein in saliva. And here I want to take our attention to the numbers of these proteins. So here I am at the RT-PCR detection limits. This is at attomolar regimes. Our sensor is able to compete with RT-PCR because you see these concentrations are already showing, this attomolar concentrations is already giving a sensor response that is well visible and distinguished from the sensor background noise. Now, the next step again was to test the performance of these sensors with actual patient samples. And to validate the sensor performance, we got patient samples from the nearby hospitals, both nasal swabs as well as raw saliva samples from SARS-CoV-2 negative, COVID-19 negative and positive patients. And the sensor is detecting the virus in unprocessed nasal swabs and saliva within 10 minutes. as sensitive as RT-PCR, so we have perfect matching with them, but again, as fast as the lateral flow assays. And I need to say that we haven't done much optimization for sample collection protocols, and I think if we do that which we are currently doing for raw saliva, we will be reaching better sensitivities. But there's, however, still some room for improvements. For example, by changing the way how we immobilize the biorecognition unit on the sensor surface, we managed to bring some extra features to the sensors. For instance, if we don't use this HTT, this carbon chemical layer to anchor the protein, but instead if we use a protein, a peptide, sorry, that has a cysteine termination, we can anchor directly the nanobody construct on top of the gold surface. And we saw that this is very useful to lower the background noise, which HTT, some uncovered HTT, is giving, especially in very complex samples such as wastewater. So for these cases, we see the advantage to use a direct coupling of the peptide unit to the gold electrode surface. So not only we are lowering the background noise, but also not using this carbon linker at the surface is giving us sensors that have long shelf life. So we can keep these sensors for various days in their buffer, and the sensor sensitivity is only affecting minimally compared to the sensors that we are building from this HTT coupling. Another area where we improved is the sample incubation step. Initially, I was telling you that we were putting the patient sample on the gate electrode surface and then leaving it for 10 minutes there. But to improve a bit the mixing, we were doing a few pipetting steps in and out to increase the diffusion, obviously, of the virus and the viral proteins to the sensor surface. But this step is not optimized and it can cause a lot of error and sample-to-sample variation. So one way to mitigate that is to do mixing externally, making a new gate electrode design, which allows us to generate an AC electrothermal flow in the sample mixture that allows the target proteins. So this AC field is causing a micro-steering effect in the solution that allows for the target proteins to come and bind to the surface. They are captured and some non-specific ones are thrown out. So this lowered the detection time, which was also the longest, the sensor speed limiting step from 10 minutes to 2 minutes, as well as it also improved the selectivity of the sensors that we built. And my last slide will be about the fact that these sensors are quite modular, because there's a particular assembly protocol of these biorecognition unit to the surface. Now, all you need to do is to change the nanobody to make these sensors selective to another target protein. Our original sensor development was for a green fluorescent protein. Then I showed you the results with SARS-CoV-2. You can do the same with SARS-CoV-1. We also did sensors for MERS spike protein. So it takes about 2 months from design to sensor, as long as the nanobody sequence exists. So this will also allow us to do more multiplex sensors in our device designs. So hopefully today I managed to show you that organic electrochemical transistors are very promising devices to do analyte detection. I showed you an example of proteins, how we use large gate electrodes with high receptor coupling density, and how this allowed us to do detection at almost physical limits for proteins. With this, I would like to thank, of course, all my group who was involved in this work, the biochemists who came up with the nanobody constructs, the polymers come from Oxford, and a few other collaborators in the kingdom that allows us to test our devices in the field. Thank you so much for your attention. I hope I'm not exceeded my time. I'm looking forward to the questions.
Thank you so much.